Hey, this is lecture 2 of chapter 11. We stopped last time right as we were starting to get into the nitty-gritty of momentum. So let's kind of pick up where we left off. We said that we had a change in momentum, this mvf minus mvi. We also said that that was equal to the integral of f of t dt, right? F of t dt from some time 1 to time 2. We said we drew parallels. There were parallels here of this change in momentum to a work or a change in kinetic energy, right? Now we said with work that was a scalar. We kind of hinted to that in the intro video, that work and energy are only in scalars, which is really convenient to work with, but we lose some of that vector information, that dimensional, directional information. And so with momentum, though, we actually still have that vector in place. Those MVs, right, those Vs are actually vectors. So we said that that was a change in momentum. Let's actually define momentum. Momentum here. Momentum is going to be defined as the variable p. Why is it p? I have no idea. All right, but we're starting to run out of letters as it is. I guess they were afraid of using m since we're using that for mass so much. That's understandable, but p seems a bit weird. Anyways, momentum is usually written as p, lowercase p. It is a vector, and it's equal to m times the velocity v. So this is a vector. That's really key here. Momentum is a vector, and it's a measurement of mass and movement, much like energy was, like kinetic energy, but kinetic energy was a scalar. This is actually a measure, vector quantity here. All right. So what we're saying with this equation that we came up with last time is that our change in momentum is equal to this integral from t1 to t2 of f of t times dt. All right. And it kind of goes in reverse too, right? I could take a derivative. I could say dp dt, right, would give me my force, right? And that makes sense. If I think about p, right, I'm saying dv dt times m. Well, that's just ma, right? That's ma. So really, it's what we have. It's everything's working in conjunction with one another. Everything is smooth. We can get back out what we put into it. This is looking good. So momentum is a measurement of something's mass and something's movement, right? Now here's a question: can a car and a baseball have the same momentum? And the answer is yes. Yes, it can, depending on how fast they're moving, right? If you think about a car moving at about 12 meters per second, that's about 25 miles per hour-ish, and think that the mass of a car is about 1,300 kilograms on average. Well, baseball is on average only about 145 grams. It's actually not that heavy. And so I would really need to be moving that baseball really, really fast to have those momenta equal to one another, right? I would basically be needing to go about 3.5 times faster than the orbital speed of the Earth around the Sun for that baseball to equal the momentum of a car moving 25 miles per hour. So mass plays a really big kind of really big factor into all of this. It's not just about the speed. In kinetic energy, it was a lot about the speed. The mass still was there, but we were squaring the speed. Here, mass and speed are really equal to one another. So a lot of times when we're thinking about momentum, it's not just how fast something's going, but how much weight, how much mass is behind that thing as well. So next time I want to dive into this delta P a little bit more. I want to talk about what delta P is. Just like we had a name, right, for the change in kinetic energy. We called it work in Chapter 9. We're going to call the change of momentum something special in Chapter 11 here, right? We're going to call it impulse. That's for next time, and I don't want to spoil the next lecture. So I'll see you back here in just a bit. Thanks for watching. If you have any questions, shoot me an email, swing into an office hour. Have a good one.